questions. Let's see, before I take any questions, let me just say, I know a few of you have asked for a little bit of extension, so that's fine. You know, I want you to be able to understand this principle and be able to do it. And typically, you know, I would highlight that there are drops in the syllabus that we talked about, but it is have a little more lenience. So I will move the time back to later on today. So with that, are there any questions for anyone?
Yeah, I had a few questions.
Anthony?
I wasn't so confident on choosing an efficiency after I graphed like the headline.
Okay. So let me let's see. So you're just not exactly sure where it falls in between, is that?
Yeah, or like what line I should be looking at.
Okay. So let's see if I have an extra curve in here.
We're going to do some soil testing today.
I dug up the old labs, but
Oh, I actually had dug them up. I totally forgot to bring them.
I guess they're in the notebook somewhere. But
We got a little side conversation going on here, so you might want to mute your microphone. Okay.
It sounded like Sam, but hers is muted.
Sound like what?
It sounded like Sam, but it's muted.
All right. So here we have a pump curve, and so I want to highlight the efficiency curves on here, which aren't the greatest, a little hard to see. But imagine, if you will, that these are contour lines, because essentially that's what they are, okay? So anywhere between 80, this one's 85 and this one's 86. So anywhere between those two lines, safe practice is to use the lowest, unless this gap is huge. You know, if the efficiency is jumping by 5%, a 2%, I guess you could probably say I'm halfway there, so I'm going to pick the middle. But if they're 1%, just go with 85. So if you're anywhere in between these two curves here, you go with 85. If you're anywhere in this point here, you're going to select 86, unless you notice that this little cross right there, I don't know if you see that very well. That little cross right there says that's 87. If you happen to nail that right on, go 87. But quibbling over 1%, you know, arguing over 1% is not worth your time. So if I fell anywhere in here, I'd say 86. Anywhere between these lines, 85. Anywhere between 85 and 84, I'd call that 84. And then we get down here to 84 and 82. Now that's when you may want to start to interpolate a little bit. If you're halfway, call it 83. And then when you jump from 82 down to 78 right here, then you could also, you know, that's a jump of 4. You could also interpolate between those as well. All right. So if there's a couple of percentage points, interpolate. If not, just go with the low one. You know, there's an old adage that goes something along the lines of, I just forgot how it goes. Under promise and over deliver, right? You guys have heard that before, some of you. Under promise and over deliver. So if you're doing this for a client and you try to squeeze out the highest efficiency and then the pump is off, your reputation's not so good. But if you tell them it's a little bit lower and it comes in better, then they're happy, right? They're like, oh, this is cool. We happen to get the good one off the line. So don't worry about that 1%. So does that help a little bit, Anthony?
Yeah.
Okay, Laura?
So if, two of your lines fall within the same percentage, would you pick the one that has a higher flow rate or?
Okay, so let's clarify. Two, like there's two pump
So-
impellers.
So I have my system curve
Uh-huh,
and it crosses, with the pump curves. And then two of those pump curves are in the same efficiency.
okay. So two of the pump curves meaning two of the different impellers.
Yeah.
Okay, fall within the same efficiency.
Yeah.
So
And you
at
wanna
that
pick
point,
the one with the highest efficiency.
right, both fall within the same efficiency. Then it's a judgment call of, do I need the higher flow rate? And if I need the higher flow rate, go with the bigger one. But if you don't need the higher flow rate, the concept is this: if I'm going to pick the higher one, but then I'm going to stick a valve on my system that constantly has to burn that additional energy up, I haven't really gained anything, right? So I could go with the lower one and actually put on a smaller motor and be okay. But if the higher flow rate is needed at any time, then you go with it and still use the valve. And so it's a little bit hard of a question to answer in the sense that you have very little information on the system, right? I mean, we've got a little book problem here, if you will, that says go ahead and do this. But in a real life situation, you're going to know the entire system of how this fits in and where it goes and what it's trying to do. And what is the range of operation? We're picking one point for operation. Pumps generally operate on a range of conditions. And you have to make that judgment call. Okay. Okay. Any other questions? Anyone else? Those online?
There were some other dashed lines on the pump curves that we had that had different horsepower ratings. What were those secondary lines for again?
Okay. So let me see if I have one here. Okay, this one here has. Oh, this one has it too. Because that's the exact same one. Let me just blow this up so you can see those. Oh, whoops, we were blowing up. So you're talking about these dash lines right here. You kind of run down through it.
Not the ones that are the impeller curves, but the ones that are below it between the dot dash, dot dash, dot dash.
Yeah, dot dash, these two right through here. And they come down to this rating down here that tells you that if you're down here with this dot dash, 121 horsepower motor, that what they call their 820 motor, is sufficient. And if you're up to the next one, you want to go to the 150 horsepower motor. And then they've got some other arrows up here says, well, but if you're up on this upper line, you're going to want to be the 295. And if it gets any higher than that, you want to go, I don't know what that 3306 is, to be honest. So basically the 154 will handle all the way until you get out here where you're going to need the 295, supposedly. I don't trust those too much. I prefer to do the calculation myself to figure out what I need, but that's supposed to be a quick reference of what motor do I need with my pump. Okay. Now I would note that not all pump curves look like this. And our discussion here, once again, before I leave that, any other questions on pump curve basics? If not, let me kind of expand on the question of what are these other lines and so forth. So let me just go to Google here. And see if we can find. Okay. Images. I should probably print one of these out because every year it gets harder and harder to find what I'm looking for. But this right here, if I can bring that one up, that's a video. I don't really want a video, but the picture there, I didn't want to start. I want that picture to start. And now it's gone. All right, right here. Okay. So sometimes this is how the efficiency is shown. Okay, so here's the pump curve, the green line, and this red line here, or orange, whatever color that is not the system curve, that's the efficiency curve, which means how do you read that? Well, you read that by everything is based on the flow rate. So if I'm doing 9,000 gallons per minute, I would come up here at 9, and that would be then my operating point. If my system curve came up and crossed right through there. Let's give this a try here. So this is not going to work, is it? It's going to turn that on.
You could maybe take a screenshot.
Well, that's an idea. Let me pull this up a little bit here. Okay, excellent idea. All right, now get this pen to work. Come on. Red. There we go, blue. I push the red button and get blue. That works. Come on.
It's grabbing there.
Yeah. Cancel. Probably got to get some training on this thing, so I know what I'm doing. But let's try this again. If you could see my screen, I'm about 5 inches away from that. So this is going to be really interesting. Here we go. Follow a little blue dot there. Try to follow that up. All right. I'm not on top of that graph yet. Yeah, I finally made it to the axis. Okay. So this then is going to be the operating head right there. And this is going to be the operating point. But I noted that we always follow the flow rate. So I would then come up directly up right there, and I would read over then, and I would note that this pump at that point is operating at 80%. So the flow rate, because note, if they use the head to define the efficiency, well, then there's two possible efficiencies, and you're using the same axis, so that doesn't make sense, right? So if you see a pump curve like this, which they exist, always use the flow rate as the measurement point, because the flow rate determines the efficiency, okay? I don't know. I'm going to be able to get rid. Okay, there we go. All right, so let me come back now to the pump curves and refine. Used to be a few years ago. This is the only one that would come up. Maybe change my wording here a little bit. Oh, here we go. This is what I'm looking for. Okay. Where'd that graph go? It's going to be on all the pages, huh? Fine, let's go back to Google search right here and
You just right click the image.
view image. Okay, thank you. Yeah, sometimes, you know, when you're up here, you don't think about that when you're with other people. Okay, so you look at this concept and like, what is going on there, right? This is just a mess. And how are we going to read this? So remember that a pump curve is for a single pump, but the number of pumps out there, there's hundreds of them, especially when you start talking about different manufacturers and so forth. And manufacturers have software now. That's pretty obvious that in this day and age, who's going to use this stuff if we have software? We're going to bring up a little software tab, we're going to punch our numbers in, boom, it's going to spit out a pump. This is where you need to be careful sometimes because the software finds one point. And what happens if your pump, so what this is right here, this is a way of finding the best pump that you should look at the pump curve. Okay? So in other words, if I know that I'm going to have, let's deal with down here in gallons per minute, I'm going to run, say, 300 gallons per minute, and I'm going to have a head of about well, let's go 200. So let's see if I can get this to work again. So I would come up. The button, open the menu. I don't want that menu. My little cursor, it's not showing my little dot. Anyway, just follow my mouse there, okay? So 300 gallons per minute, I come up here to 200 feet and I land on that pump that is 3x2-8. Now, in this specific manufacturer, that's going to mean something. It probably means, well, you know what? I'm not going to take a guess at what it means. Usually it has something to do with the intake size and the exit, but I'm not entirely positive. But what this is telling us is that's the pump that we want for this particular flow rate and head, all right? And so I'd pull out that pump curve and I would plot everything up and I'd see how it'd work on that pump curve. Well, that's fine and dandy, but that's one point, that's one value. What happens if we know that we're going to range down a little bit and maybe most of the time we're going to be operating over here in the 3x1-8 or whatever that is over there. And so you can get these very narrow operating ranges, and that's what the software is going to tell you. But if you look at the whole performance of your pump, or the whole performance of your system, I should say, that does not necessarily mean that that pump is the best one. And usually when you talk to a pump salesperson, a representative of a pump company, they are not an engineer. They're very competent at what they do, and I trust them for what they do because they know pumps left and right. They don't know your system. And so they may give you, they'll give you the one point that you think is the best, but understanding the whole system and how it fits and why one of these other pumps, if you vary a little bit in your flow rate or your head, why one of the other pumps may be better. So you might want to look at, 3 or 4 right in here, plot the pump curve and verify that you have the best one. Okay. All right. So given that information now, let's go back and learn another piece of information. So one of the things that was on our pump curves that you figured out how to find, but you don't understand what it is yet, is the net positive suction head. Well, now how did that happen?
When you move the Zoom people, it like drew one.
Is that the, well, where's the erase button now?
I think it
Oh,
was.
now it just erased. Okay. All right, I'll just keep my mouse off of there. All right. want to talk about still not on there. Zooming out. There we go. Okay. Talk about the net positive suction head. NPSH. Okay. And this is a very important concept when it comes to sizing or getting the right pump, because this will ruin the life of the pump if you don't get the net positive suction head correct. Now, this is an interesting term. Positive suction. There seem to be at odds there a little bit, because we expect suction to be negative, and we're talking about positive, so net positive suction. So this is the concept of net positive suction. Pumps are spinning. We're talking about radial pumps, centrifugal pumps. They're spinning, and the fluid has to come in and lay down on the blades for the blades to impart motion or to impart energy to our system. And when they do that, they move the water away very rapidly. You know, it's like a tow rope is coming along, and you're off to the side, and all of a sudden you decide you want to grab hold of that tow rope. It's going to jerk you forward, and if you have a friend standing next to you, they're left there, right? So the blades grab the fluid and move it, and the fluid right next to you is still there. They may fill your gap because the blades create a suction. But if it's too big of a suction, then we get cavitation. Cavitation is the rapid change of a liquid of a fluid, and I guess we have to be a liquid, from the liquid phase to the gas phase. All right. So cavitation forms little air bubbles, and I think we may have talked about this a little bit, but I'll review it. It forms a little gas pocket. So it's not an air bubble. I got to be a little careful with my terminology. So if we're going with water, it forms water vapor, just like when you're boiling water. It's water vapor, and that water vapor is in a bubble, and as the pressure continues to go more negative, that bubble grows and grows and grows. And then when you get on the other side of the impeller, all of a sudden you hit a high pressure, and that bubble collapses. And this is a rapid phenomenon. It occurs very quickly. It's an implosion. So explosion blows things out, implosions blow things in. And a couple of things happen when you get an implosion. It's just as powerful as an explosion. Fortunately, inside of pumps, they're little tiny bombs, if you will, okay? Little tiny water bombs going off. But due to the way they implode, you get vibration is the first problem. And the vibration can be very powerful in the near area. And it also creates a water jet because it implodes inward. And that motion inward then creates a high pressure water jet. And I don't know if you're familiar with water jets in industry, but they can use water jets to cut through steel. You can cut through a plate of steel with high pressure water. And that's in essence what you're doing is this water jet then, if it's close to a surface, will go and cut off a little piece of the surface. Now these are tiny, tiny little pieces, little pinpricks, if you will. One of the things that I never was involved in it, but when I was a student, one of the faculty members was doing research on cavitation. And the way they do it is they put a aluminum liner or aluminum blank, I called it a blank, but it was part of the liner inside of the pump. It was just a thin sheet of aluminum. Not necessarily thin, but it was a nice polished piece of aluminum that they would slide in there, and it was flush with everything. And then they'd cavitate the pump, and then they'd pull that out, and the graduate student that was working on that got to go in and count all the little pinpricks on that piece of aluminum. And they put a little grid on it, and they'd count all of them up, and pretty tedious work, but it gave some idea then and of how fast the cavitation was damaging the material. Okay? And what you had to do to stay away from that. So in order to prevent that, what we want to do, we want to make sure that there is sufficient pressure on the intake side of the pump to push the next particle of fluid into the pump blades so that you don't create that cavitation, all right? And so that's why we call this the net positive suction head. Now, if you remember from first part of the course, or going back to your basic fluids, we have some datum down here. And this datum is P is equal to 0. And I guess we don't need to put units on that. It could either be in the metric or the English system. P is equal to 0, but we're going to put ABS, absolute. So at absolute 0, we have no pressure. There's no molecules there. And then if we come up here a little ways farther, we have then P atmospheric. So P ATM, P atmospheric. And a lot of times we reset our datum. So P atmospheric is equal to 0. So we say, you know, right now the pressure that we feel is 0, but it's really not. You know, if we're at sea level, 14.7 pounds per square inch, 101 kilopascals, variety of other measurements, so many inches of mercury and so forth. That then is the atmospheric pressure, right? Now we have another pressure down this direction here that we call the vapor pressure, piece of vapor. Piece of vapor is when we get the rapid change from liquid to gas. All right. Now, as we pull fluid away, we're actually creating a negative pressure because pressure and velocity are inversely related. High velocity, low pressure, right? Like when we go through a Venturi meter, you speed up the velocity so you get low pressure. So here, when we're pulling the fluid away, we get extremely high velocities because we're moving it really fast now, and the low pressure is on the back side. So we have to make sure that we have sufficient pressure here. This is the pressure to move fluid to the pump. So anytime we're dealing with net positive suction head, that should be a clue to you that you want to use absolute pressures. You stay away from gauge pressures, use absolute pressures. Just like when you're doing the ideal gas law, use absolute pressures, okay? And so we could actually write the energy equation and we could derive the net positive suction head. But let's jump back to that pump curve. Okay, so I'm going to throw this pump curve up here, and down here we have NPSH, and then subscript is RE. Okay, RE means required. So our goal is to make the net positive suction head available greater than or equal to the net positive suction head required. I'll put a little RE down here. And over here, we usually just use A. NPSH sub A, we want that to be greater than or equal to what is required. Now, you have to be careful. If you put it equal, that means you're trying to go right to the limits of your pump. All right? And let me give you a little thought concept here. Let's say it was down in California and we had a system. We put a pump on that system. And the pump worked great on that system. And we came up here to Idaho and we had the exact same system, same temperature of the water, same pipe length, same everything, lifting at the same elevation, and we stuck the pump on this system and it didn't work as well. Why?
Lower atmospheric pressure.
Lower atmospheric pressure, yeah. We are at a higher elevation, so we have a lower atmospheric pressure. We're talking about net positive suction head on top of our P is equal to 0 here, our gauge pressure. We have this atmospheric pressure pushing down, okay? When you're sipping on your soda through a straw and you create that suction in your mouth, it's actually the positive atmospheric pressure pushing the fluid to get to you. So we have this positive atmospheric pressure pushing the water into the pump. But if you go to a higher elevation, you don't have as much. and it's significant. I haven't looked, I always forget, but you know, sea level, we say 14.7 on average. It varies whether you have a high pressure storm system or a low pressure storm system coming across. Pocatello, anyone have any idea what we're sitting at right here? I think it's somewhere right around 13. I could be wrong. Yeah, we could look it up really fast, but you know, and it varies. We've been as low as 12, I think 12.7 or so. But we have this fluctuation, and you think, well, that's no big deal, 1 pound per square inch. Well, you get something that's 100, you know, 1 square foot, that's 144 pounds right there. 144 pounds difference pushing that fluid. Okay. I don't know if any of you have ever experienced the effect of going to a higher or lower elevation. You know, it's actually pretty cool if you go from high elevation to low elevation. You know, this summer I got to go work in Alaska. Moved from Utah to Alaska. The first 2 weeks was just beautiful. We could go play basketball all day long, and it's like never got tired. But it didn't take long for my body to adjust, and then it was gone. But so it's a real thing, right? So when we go ahead and pumps, there is no theoretical way of figuring out. We can approximate, but we can't figure out what is the net positive suction head required. So when we design a pump, we take it down to the lab and we run it, and there's standards for saying, okay, this is when cavitation starts. And so with that, then they plot up this net positive suction head required graph. Okay, now I'm going to show you how to calculate the net positive suction head available here in just a minute. But a little caveat here, a little word of warning. 2 pump manufacturers, the pumps are identically the same on the performance as far as the head and the flow and the efficiency. One pump manufacturer says, you know, I'm going to push that net positive suction head down as low as I can go because that's going to make my pump look like it is the better pump because I have a lower NPSH required needed. So be careful. I mean, some pump manufacturers may, you know, 1 or 2 more percent. Let's see if we can squeeze that out. And so that's why you don't want to be, both the weather can change and pump manufacturers may try to squeeze the last little bit out. And I don't blame them, but you know, as long as they stay within the standards and they're legitimate, but you want to try and be higher available than not so you don't run into any problems. Okay, so there's a lot of different equations for calculating the net positive suction head available, but I'm just going to use the one in the book since that's our reference. I say if you grab another book, some people derive it slightly different. This is perfectly fine. And this one tells us that the net positive suction head available is equal to the atmospheric pressure, P atmospheric, divided by gamma. So this is the atmospheric pressure head, plus any change in elevation, okay, to the water surface, and we'll define these in just a minute, minus the vapor pressure head, because the vapor pressure head is not available to help us. This distance down here, when we're going from absolute 0 up to the vapor pressure, that's not available. That part of the atmospheric pressure is not there to help us. So we have to subtract that part out. Plus, we lose energy of the flow going into the system. Okay? And so we have to subtract out then the velocity head. I'm sorry, we have to subtract out the head loss. The velocity head is still there. We are subtracting out the total head loss, which includes the entrance loss, any minor losses such as elbows that is in our intake, and any friction loss, because that is going to reduce the amount of available energy in our system. So taking the atmospheric pressure, what's available, adjusting for any elevation, and when I say elevation, this is the elevation of the pump relative to the water surface. I'll draw that up here in just a minute. Subtract out this little difference here on the vapor pressure and any head losses going up through our system, and that'll tell us how much is available, and we want to make sure that that is greater than the amount that is required. Now, the one thing that we can change in our system easily, well, there's a couple of things we can change, but the one thing that's very easy is this delta Z. Where is the pump in relationship to the water surface? Okay. So the question is, pump in relation to water surface. And this is why you have to be careful on which book you use, because like I say, they can define these differently. If here's my water surface, okay, here's my water surface, and I'm going to put 2 pumps here. Let's see, so this is my tank. And I'm going to put a pump right here. I'm going to come down here on the bottom, and I'm going to put a pump over here. Okay. So pump A and pump B. So piece of A and piece of B. Okay. So Z, okay, this is relation to the water surface. So if I go above my water surface, I'm actually lifting the fluid above the water surface, and that's going to take additional energy. So any kind of a lift of the water surface up to the center line of the pump, that right there is going to be a negative Z. And going down in the other direction to get to the center line of the pump, because I have all that water above my pump, and all that water is adding additional head to push the fluid, to push the water into the pump, that then adds to the net positive suction head available. So if I stick my pump down in the water, I have more net positive suction head available, because there's additional weight pushing down on it, and that's a positive Z. This is one of the biggest things with the net positive suction head, keeping this straight. But if you understand the mechanics of the equation, this falls right out. If I have to go above the water surface, that's negative, okay? If I want to find what is the location of my pump, I let the net positive suction head equal the net positive suction head required. Go ahead and solve for delta Z. If I get a negative Z, that tells me how high, the maximum height I can put my pump above the water surface. Now, I'm going to probably want to come down a little bit for safety. If it tells me that I have a positive value, that means I have to be underneath the water surface to get the correct value. Okay, so to solve, our solution method is we let the net positive suction head available equal the net positive suction head required. And then find Z. Negative Z is placement above water surface. Okay. Positive Z, we need to be below. Oh, thank you. Let's hurry and see if we can do this example. Any questions first? Okay, so I did post this to Moodle, and so this is actually from an old test. Pump is installed at a supply reservoir. The following describe the design conditions. The flow rate is 8 CFS. The water temperature is 50 degrees Fahrenheit. The site elevation is 5,000 feet, which from that we get the barometric pressure of 12.3. Okay, the suction diameter is 12 inches. The entrance loss, we have entrance loss, we have an elbow, we have a friction loss, and the pump requires a net positive suction head of 20.5 feet. This is from the pump curve. Okay, and based on the net positive suction head, we want to find the maximum height from the water surface the pump should be installed. The first thing we need to do is we need to find the vapor pressure then, or the vapor pressure head. So we would go into a book and we would look this up. Find the fluid properties in this new book. I'm not sure where it is. In the old book, it was in chapter
Page 74.
74? Okay. Great, thank you. So at a maximum water temperature of 50 degrees, okay, we come in here and we find then the vapor pressure. And it's noted as vapor pressure head. So 0.41 feet. Okay. So in this particular instance, P sub V over gamma, 0.41 feet. All right. So I'm going to let the net positive suction head available equal the net positive suction head required, and that's going to be equal then to my equation. So I'll bring that equation back out here, where we said P atmospheric over gamma plus Z sub S minus P sub V over gamma minus the head loss. Okay. Well, simplifying our equation, we know that the net positive suction head required, 20.5 feet. Okay, the atmospheric pressure, we just defined that as 12.3 pounds per inches squared, and so we need to convert that to the correct unit. So we're going to divide by 62.4 pounds per cubic foot and multiply the top by 144 inches squared per 1 square foot. And P sub V over gamma goes to 0.41, and I still need to calculate the head loss. So we know head loss then is equal to the quantity F times L over D plus the entrance loss, which is going to be 0.9, so this is K sub L, plus the minor loss coefficient, so 0.7. This is K of the elbow, right? Kind of small there. And F times L over D goes to 0.3, right? And all those then are going to be multiplied by Q squared divided by 2G A squared. And of course, Q is 8 CFS, and the area is pi divided by 4 times 8 divided by 12 squared, and then I'm going to square that whole thing. So given that right there, I can crank this out.
Sure you convert your 12 to
You sort of do what? Sorry?
oh, it's 8 over 12?
Yeah, 8 over 12. Yeah. Okay.
Number was just 12 inches.
Oh, it is. Why did I get the 8 feet? I don't know where I got the 8. Thank you. Yeah, so that makes life easier, right? Thanks for that correction, because I would have the wrong answer. Okay, so 864. So if I've done that right, I get my head loss is 3.1 feet. Okay, so now I'm going to have 20.5 is equal to, and collapsing my atmospheric pressure, or simplifying that, that's 28.4 feet, plus Z sub S minus 0.41 feet, minus 3.1 feet, okay? And so now, solving this equation, I get Z sub S is approximately equal to a negative 4.4. So what does this tell me? Where do I want to locate this pump relative to the water surface? Or what is the maximum height that I can lift this pump and still have it working correctly? Yeah, so this much above the water surface, exactly, yes. So the negative sign means that I can go above the water surface 4.4 feet. It would be better to drop it down to, say, no more than 4 or 3 feet above the water surface, just to have a little bit of a factor of safety built in there. But that's what that tells me. If I've done those numbers correctly, I may have punched things in incorrectly, but the concept of getting a negative value tells me then that I can go above the water surface. There are some pumps that require a pretty significant net positive suction head, okay? So make sure that you always go, that you're always conservative and always place the pump a little bit lower than what your calculation tells you. All right? Scott, how did I do on that number? Is that punching in that?
Yeah, the atmospheric is where I'm getting a deviation, a little about when we calculate it.
So 12.3, 144 times 62.4, 28.4.
Yeah, we're good.
Yeah, okay. All right, so with that, I will post some problems for you to do with net positive suction head. Be due on Tuesday, right? Monday, we'll talk about pumps in series and parallel. And then everything after Monday, what we talk about on Wednesday will not be on the exam. And on Wednesday, we can review. With that, have a wonderful weekend, and we'll see you on Monday.
Also, I don't think you posted
I haven't posted that,
this.
didn't I?
It's not on here.
I wonder if I forgot to hit save. That'd be just like me. Forget to hit save.
Yeah. I don't see it.
Well, that's the advantage you get from coming to class.